Hello and welcome. This is Michael Annis, and you're listening to episode 96 of the Space Rocket History Podcast. And now, Soyuz Test Flight Number 1, Kosmos-133. Recapping from episode 95, after many delays in launching the first Soyuz due to design complication, delays in equipment deliveries, the learning curve for testing new designs, unreasonable launch dates, persecution from the Communist Party, and the death of Chief Designer Korolev, the first unmanned test flight is nearing launch. 2 Soyuz 7K OKs have made it through testing. Both Soyuz have been attached to their carrier rocket and are ready to launch. The plan is to launch both vehicles 24 hours apart in order to perform a rendezvous. On the morning of November 18th, at launch site number 31, Chief Designer Mission held a meeting of the technical leaders. They decided to propose launching the unpiloted pair of Soyuz 1 day apart. The active Soyuz on November 26th and the passive Soyuz on November 27th. According to the factory rendezvous documentation, the active Soyuz vehicles were assigned even numbers and the passive ones odd numbers. But, according to the news service TASS, the Soyuz were numbered by the order in which they were inserted into space, and the unpiloted vehicles were referred to as Cosmos vehicles with the corresponding numbers. If, after orbital insertion, the passive vehicle turned out to be more than 20 kilometers away from the active one, which was quite likely, then the command would be given right then and there to activate the EGLA to begin search and rendezvous. If the distance between the vehicles turned out to be more than 20 kilometers, then ground-assisted special maneuvers would be necessary, and rendezvous would take another 24 hours. After rendezvous and docking, there would be a test of the controllability of the uplink established between the two vehicles in space. The plan was to undock on the third day and then 24 hours later execute the controlled landing of both vehicles. Before we go too much further, I want to briefly cover the launch vehicle for the two Soyuz. The Soyuz 11A-511 was a Soviet expendable carrier rocket designed by OKB-1 and manufactured by State Aviation Plant No. 1 in Kubashaev. The 11A-511 introduced a new uprated core stage and strap-on boosters, which became standard for all R-7-derived launch vehicles. It was a two-stage rocket with 4 liquid-fueled strap-on boosters clustered around the first stage and a Block 1 second stage. The 11A-511 was 45.6 meters high and 10.3 meters in diameter. It weighed 308,000 kilograms and was capable of launching 6,450 kilograms into orbit. Stage 0, the strap-on booster, could produce 994 kilonewtons of thrust. The first stage produced 978 kilonewtons, and the second stage produced 294 kilonewtons of thrust. This was the first launch of the 11A-511. The model would eventually be used for the first 19 manned launches of the Soyuz program. Now let's consider how the Soyuz would be tracked and controlled. Tracking stations were scattered throughout the Soviet Union, but the ballistic centers equipped with computers that made flight control possible were located in Moscow. Moscow had decisive advantages. Subsequently, control centers for both piloted and unpiloted vehicles were created near Moscow. The full State Commission were duty-bound to gather at the Cosmodrome to make the launch decision. After determining that the spacecraft had been inserted into orbit, the members of the State Commission would board their airplanes and scatter, some to remote tracking stations and some to Moscow. The problem was, the State Commission could not be in session all the time and make decisions, much less real-time decisions. To solve this, operations control groups were formed. Group T, stationed at Tyurtam, the Cosmodrome, Group YE, stationed at Yevpatoria, Tracking Station 16 in the Crimea, and Group M, stationed at Moscow. Initially, Chertok was appointed chief of the group at Yevpatoria. His deputy, Pavel Agasanov, simultaneously commanded all military forces involved with control. Agasanov was endowed with talent as a good organizer and enjoyed the rights of deputy commander of a military unit, which included all the tracking stations, communication facilities, and the computer center. Agasanov, in effect, was the flight director. But there was a problem at Yevpatoria. At Yevpatoria, there was no means for automatically processing and visually displaying flight information in real time. The main means of receiving flight data and transmitting flight commands were secure telephone and telegraph communications, which was a serious handicap. In fact, when the Soviets saw NASA equipped with dozens of electronic screens at mission control centers at Cape Canaveral and in Houston, they could hardly believe it. So, the flight director was stationed at Yevpatoria and only had telephone and telegraphs to communicate flight commands. Almost unbelievable. Okay, on to the launch. Finally, after years of hard work and struggle, it was time to prove the Soyuz. For the first two Soyuz, Mission and Chertok arranged that before the first launch, all the main forces would be concentrated at the Cosmodrome. Immediately after the launch of the first active vehicle, Chertok was supposed to fly out with a group to Yevpatoria to join Agasanov to monitor the rendezvous and docking process from there. After the launch of the second passive vehicle, the chairman of the State Commission and anyone else who wanted to would also fly to Yevpatoria. Now the launch. On November 28, 1966 at 11:02 Universal Time, the first Soyuz, the active vehicle, successfully launched into an elliptical orbit of 171 kilometers perigee and 223 kilometers apogee. During the launch, Mission, Chertok, Bushayev, Feoktistov, and all the other chiefs waited in the bunker at the launch site number 31. They were waiting for reports that the 7KOK had successfully entered into orbit and the solar arrays and all the Eagle antennas had deployed. When the reports of initial success were received, everyone ran to their cars heading for launch site number 2. Chertok rode with Bushayev. They were both in an excellent mood to see the opening of the Soyuz era. Bushayev and Feoktistov had extended a great deal of effort to slow down manufacturing work on a series of unpromising Voskhds in favor of these Soyuz. Now that the Soyuz era had begun, they believed a mission would soon be assigned to catch up and perhaps surpass Gemini-based records on the number of cosmonauts and dockings and flight durations. It was a very happy car ride. However, by the time they arrived at the command post, Mission was already questioning the telemetry operators. They found out that after separation and before leaving the radio coverage zone of the Far East tracking stations, the Soyuz had not settled down. An inexplicable spin continued. About 10 minutes after their arrival at the control center, having flown around the globe, the new spacecraft entered the tracking station number 16 radio coverage zone and then the coverage zone of the local tracking station IP1. Both reported that all facilities were experiencing stable receptions and good signal level. An agonizing period of silence set in while all the telemetry operators at IP1 were trying to reconcile their visual impressions. They had a lot of experience with the launch vehicles, and there was unusual information coming down from the Soyuz, from the new BR-9 telemetry system. They were the first to suspect a problem, but were afraid to report without a thorough checkout. Kirillov demanded permission from Michelin to roll out and prepare the second launch vehicle with the passive Soyuz. Less than 24 hours remained before the second launch. The launch crews and all the firing range services, inspired by the successful launch, were prepared to go without sleep for one more day for the sake of the long-awaited resumption of Soviet space achievements. The commander of the auxiliary aviation was keeping airplanes at the ready to depart for the Crimea and Moscow, and needed answers to the questions, are we flying or not? And if yes, then who and where to? Agasanov was requesting further instructions from Yevpatoria in order to prepare all the tracking stations for the next session. Tension was at its height when at last the paper rolls containing the direct recordings of the onboard system's performance began to arrive from the receiving stations to the screening room on the first floor. Telemetry service officers were trying to interpret that orientation system propellant was gone. The tanks were empty. Feoktistov asked them to check one more time. Again and again, scaled rulers were applied to the paper tapes. Doubts dissolved, and with them hope as well. The spacecraft was spinning at a rate of 2 revolutions per minute. It was a complete loss of roll stability. This meant the spacecraft had already lost all capability to execute the primary mission assigned to it. Now, since it was already in space, they needed to quickly change the previously developed programs and check out the other systems that were functioning. Chertok reported to the State Commission, quote, "There's no propellant in the DPO tanks," end quote. Replaying the data on the memory unit showed that right after separation, the approach and attitude control engines had performed a very intensive roll burn. Telemetry was corroborated by calculations showing that during an orbit in such a mode, it was possible to lose all the propellant from the orientation engine DPO tanks. At this point, it was clear that rendezvous and docking were impossible. Mission made the obvious decision: stop the launch preparation for the second vehicle. Instead of leaving for Yevpatoria with the operations group, Chertok was to make recommendations right there for a new flight program. Bashayev, Feoktistov, and Roshenbach were to find out where the DPO propellant went and why. Shabarov, Kirillov were to take steps to maintain the second launch vehicle and spacecraft. The ballistics experts were to immediately ascertain the orbit and give a prognosis. How many orbits will the spacecraft survive without correction? In addition, Karamov and Mission were supposed to immediately prepare a report for the brass in Moscow and a draft communique for the morning newspapers and a radio about the flight of Kosmos-133 instead of the anticipated Soyuz. The ballistics report was first to come back. It said the vehicle will begin to plunge into the atmosphere after the 39th orbit. Chertok proposed performing tests on all systems. First and foremost, they wanted to check the ion attitude control system and the backup correction engine, which is called DKD, to make sure that it would be possible to return to Earth with its help. The thing was that the depletion of the DPO propellant had deprived the spacecraft of the capability for a retrograde burn to return to Earth using the main approach and correction engine. Chertok began feverishly drawing up the programs for the upcoming test. During subsequent orbits, it was discovered that all the systems were completely reliable. The primary task was to test the fundamental new mode of guided descent and soft landing. If it were to succeed, then it would show that the 7K was safe for piloted flight. Despite a second sleepless night, after each communication session, the telemetry service spread out rolls of telemetry data and dozens of heads bent over them. It was discovered that the vehicle pitched and yawed in directions opposite to the ones given in commands. The gyros were issuing the right command, but the vehicle was turning the wrong way. There was obviously a problem with the DKD backup orientation engine. After a rather heated argument, it was discovered that the engine specialist and the control specialist had an opposite understanding of the concepts clockwise and counterclockwise. The Soviets had delivered into space a vehicle with two common errors. First, an error of polarity or sign, plus for minus, and second, clockwise for counterclockwise. The errors should have been detected during ground testing. This mistake was particularly painful for Chertok and Isaev, the chief of the engine specialist. It was difficult to come up with a reason to explain the causes of such technical neglectfulness. Chertok promised upon returning to OKB-1 to organize an action group for an on-the-record study. But the immediate problem was how to return the spacecraft to the ground. Someone came up with the idea to fire short bursts from the backup orientation engine so that the cumulative effect of these small braking pulses would slow down the craft sufficiently to enter the atmosphere and land in Soviet territory. About 2 days later, on the 33rd orbit, the braking burns began. But another problem occurred when the Soviets lost all contact with the spacecraft. It was neither in space nor on the ground. Then Chertok realized what had happened. The braking pulses had worked, but they had failed to consider that the spacecraft had a self-destruct system. All those braking burns did not guarantee that the vehicle would land on Soviet territory, and the self-destruct system activated and destroyed Kosmos-133. The destruction was so complete that even the air defense radar were incapable of detecting the pieces of the spacecraft. Everyone returned to Moscow in disgrace. The next day, in keeping with the rules at the time, Chertok assembled the main supervisory staff of all the departments. In his speech, he said that we should not lay the primary blame for the loss of the first Soyuz on the one who committed the error. Errors always have been and always will be committed. In our complex system, we commit them every day. The errors must be discovered during ground testing. Our testing equipment at the monitoring and testing station and the engineering facility was perfectly suited for detecting those two errors. Therefore, the primary blame for what happened should be laid on the managers who did not display vigilance and who did not insist on higher standards when developing the procedures and conducting the actual test. During the turbulent discussions that followed his speech, one of the developers of the self-destruct system spoke up. He proposed that no one be punished, but rather that a commendation be issued for the fact that through their fault they had managed to check out and confirm the reliability of the emergency spacecraft destruct system, especially since the system had never been subjected to full-scale ground testing. Needless to say, there weren't going to be any commendations given for that mission. However, there was a search for the guilty parties. It was discovered that one of the thermal mode specialists came to the conclusion that the hot jets of gas from the orientation nozzles would blow on the solar array panels. They reported this to Feoktistok. Without giving it much thought, he proposed that they turn the nozzles 180 degrees about their axis so as not to undertake a complex modification of the spacecraft. Rotating them this way changed the sign of the moment around the axis of rotation. To maintain the order in which the spin commands were given, it would be necessary to change the polarity or the phasing of the command issuance by the control system instruments. The instrumentation would have to be changed. By the time the Soviets figured out what to change, the instrumentation had already been installed in the Soyuz. The factory manager was outraged about having to remove the instrumentation, so he asked his deputy to find out why he had to do it. The result was the instrumentation never got changed, and the Soviets sent a defective Soyuz into orbit. Listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange donate button or the Patreon link. Thanks.